Hello everyone. I would ask all the speakers to come to the front, please, all the presenters. So we are still missing some spotlight presenters. I would ask them to come to the, please. One, two, three. You introduce the first page? I introduce the session and I give the mic to you. Okay, hello everyone. So we're going to start this morning session. My name is Gregory Roger. I will be co-chairing this session with Ahmed Pirsiavash here from the University of Maryland, Baltimore County. The session will be about analyzing humans. We'll have 3 talks and 13 spotlight presentations.
So the first talk is going to be DoubleFusion real-time capture of human performance with inner body shapes from a single depth sensors, presented by Tao Yu. The other authors are Zerong Zheng, Kaiwen Gu, Jianhui Zhao, Qionghai Dai, Hao Li, Gerard Pons-Moll, Yebin Lu. Please line up at the microphones. There are 2 microphones in the middle of the hall. Please line up after the talk for questions. Thank you.
Okay, thank you for the introduction, and good morning. My name is Tao Yu, and I will introduce our work, DoubleFusion, real-time capture of human performances with inner body shapes from a single depth sensor. So our goal is to contribute a better single-view human performance capture algorithm that can not only enable convenient and robust single-view performance capture for everyone, but also benefit traditional multi-view performance capture systems. And by the way, we are not going to talk about any deep learning in this talk, so if you want to leave, now is the time. but I will convince you that we can achieve very good performance without using it. The input is a single view depth video. From the rotating fused model, you can see that we only get a partial geometry of the performer at the beginning. But as shown in the video, we can gradually fuse a complete and detailed geometry model, estimate a plausible inner body shape, and track fast motions in real time. Related work. Some works use a pre-scanned template to do performance capture by either using embedded skeleton or without it. These methods can generate accurate dynamic reconstruction results, but the problem is they require to pre-scan a template or perform skeleton embedding manually. Other methods do not need to pre-scan a template. They use parametric models instead, like Scape, Simple, and Dana, shown on the top. These methods can generate semantic and robust results, but some of them cannot reconstruct detailed geometry of the clothing. It is because the limited descriptive power of the parametric models, and the others still need dense 4D scans as input to generate high-quality results. In conclude, all of the methods have difficulties to reconstruct complex geometries and topologies. So model and template-free methods are more general because they do not need parametric models and pre-scanning efforts. Real-time dynamic reconstruction works built on DoubleFusion, which is the first real-time template-free method. However, without incorporating semantic information, this method still cannot achieve robust human performance capture using single-view setup. Is it because all of them are struggle from fast human motions? So the most related work to our paper is DoubleFusion, which is the best paper of CVPR 2015. We are inspired by this work. The basic idea is to perform energy tracking and surface reconstruction at the same time. And the main problem is tracking failures will lead to erroneous fused geometry, which in turn leads to worse tracking. And this loop makes it unstable for challenging motions. In DoubleFusion, we address this limitation. Note that dynamic fusion is for general scenes, while our method is focusing on capturing humans. So first, let me tell you a little bit about why dynamic fusion failed. Dynamic fusion defines a node graph that encodes smoothness constraints. Neighbor nodes are constrained to move similarly. During fusion, if nodes belonging to different body parts are erroneously connected, for example, the legs at here, body parts, it would force the two legs always move together, which is not real. So our solution is a double-layer surface representation that combines freeform fusion-based methods and model-based methods. The freeform fusion-based methods is used to enable general reconstructions, while the model-based methods is used to improve the robustness. To describe the multi-layer geometry and motion of the performer in an accurate and semantic way, we propose double-layer surface representation. The double-layer surface includes a parametric inner body and an outer fused geometry of the performer. For motion parameterization, we use skeleton to parameterize the inner body motion, and the double node graph to describe the surface energy deformation of the outer layer. Note that we use state-of-the-art scaled multi-person linear model, Simple, to describe the inner body. One of the key ideas is to parameterize the geometry that's close to the body with underlying simple body model. This geometry is shown in gray at here. And to parameterize the geometry that is far from the body, we use a traditional node graph similar to dynamic fusion. Here, we call this motion parameterization double node graph. It constrains surface close to the body to move like a human and leaves the far geometries free form. So problems of connecting different body parts happen much less often. The pipeline of our system includes 4 parts. We need to initialize the system after we get the first steps frame. And then we perform motion tracking to get the skeleton and surface energy deformation at the same time. After we get the surface energy deformation, we can perform geometry fusion to complete the outer surface. And finally, since the inner body estimation is not accurate when the geometry is not complete. We perform shape optimization for the inner body when the outer geometry gets more and more complete. We start to initialize the whole system after we get the first depth frame. The performer is required to start with a rough A pose, and then we initialize the truncated sun distance function, which is TSDF, using the initial depth frame. Then we estimate the initial body shape and pose by fitting the simple model to initial depth frame. After initial body fitting, we initialize the skeleton embedding of the outer surface using initial pose, and also initialize double node graph according to the fitted body. The next step is joint motion tracking. Given the current depth input, we estimate the motion field for double layer. We jointly optimize the skeleton motion and surface energy deformation using a single energy function. The energy function includes a data term that measures the misalignment between the double layer and the current depth input. It consists both skeleton and energy tracking data terms. A bounding term constrains similar motion of skeleton and node graph, which enables joint optimization of skeleton and energy deformations. A regularization term that constrains local as radial as possible energy deformations, and a post-prior term that penalizes unnatural poses. I will introduce the data term at here, and for other terms, please refer to our paper. Correspondence searching is always a very important step for robust and accurate motion tracking. This is a simple example on how the double layer can help us to track fast motions. So let's suppose the double layer is a bow. We want to deform the blue bow string to fit the current red depth curve. DensePose uses projective model to depth correspondences for real-time performance. But as shown in this figure, because of large motion, we cannot find projective correspondences. However, benefiting from the topology consistency of the inner body, we can construct a hierarchical structure for very efficient nearest vertex searching. So by searching for the nearest body vertex, we can still find closest correspondences between depth and the inner body for tracking. And after several iterations, we will deform the double layer surface to a better position, and then the projective pairs will take control. Finally, for later iterations, we get accurate tracking results gradually. After joint motion tracking, we perform geometry fusion. Here we show the input depth on the left. You can see it's noisy and incomplete. And by using the energy fusion method proposed in dynamic fusion, we will get a complete model gradually, as shown on the right. The last step is volumetric shape and pose optimization. Here we perform the shape and pose optimization in the TSDF volume directly. The energy function of optimization contains three terms. A data term that measures the misalignment of the inner body and the outer surface. We also incorporate temporal and post-prior regularization term. I will explain the data term at here. From our geometry fusion step, we can get the updated TSDF. Our insight is the TSDF of the outer surface provides a very good reference for optimizing the body model. So we can minimize the sampled TSDF of all the body vertices to optimize the shape and pose of the body model very efficiently. We evaluate the volumetric shape and pose optimization. We can see from the top row that without volumetric optimization, tracking failure and erroneous geometry fusion happens. Comparison. Here we compare our method with state-of-the-art methods. As shown in the video, our method can achieve more robust, fast motion tracking performance than the other methods. Results. Here are some results of our system. Note the detailed geometry and the fast motions that we reconstructed. And here, Please note the complex clothing and plausible inner body shape that we reconstructed. We can also enable a relatively large active area, benefiting from the robust single-view performance capture algorithm. To conclude, DoubleFusion enables convenient and robust single-view performance capture in real time. The proposed double-layer surface representation is a key of robust tracking and plausible loop closure. Because we only use a single camera, we believe our method can open a lot of applications, include AR, VR, gaming, and virtual try-on, etc. Future works include handle very white clothes, geometry separations, and human-object interactions. Thank you. For more results and details, please come to our poster.
Yeah, thank you. So any questions from the audience? Please, there are 2 cameras in the middle of the hall. Please line up. Yeah, please.
Nice work. And you don't need the deep learning. That's great. But I still want to know, it is possible to integrate the deep learning technique in your method. And what will be the benefit? Thank you.
OK, thank you for your question. Yes, absolutely. Deep learning can be incorporated into our system to improve the performance. For example, as an initialization step, currently we need the performer to start with a rough A pose. But if we use deep learning to detect the pose of the performer, as a first frame, we will enable to initialize the system at any pose. And we can also use deep learning to help us optimize the inner body shape and pose of each frame to give us a better initial value. And since our method is for capture the data, so it's very good for deep learning, for capturing a large amount of data, very efficient, and for training.
Thanks. Any other question? No question? Oh, yeah, please.
Can you estimate the computational complexity required for the real-time capture?
Actually, you mean the bottleneck of the performance?
I'm just wondering, do you have a rack of GPUs, or what's the computation required for that real-time performance?
Actually, currently we use a Titan X because we rely on very powerful parallelism computational ability. And I think it's able to also run in real time on about 1080 and 1070 graphics card.
Okay, thank you.
Yep. Thank you.
Thank you.
Okay, the next talk will be about dense human pose estimation in the wild. The authors are Rıza Güler, Natalia Neverova, and Iasonas Kokkinos. And the talk will be given by Rıza Güler.
Hello, I'm Alp Güler from INRIA and Central Supelec. This is joint work done with Natalia Neverova and Iasonas Kokkinos during my internship at Facebook AI Research in Paris. In this talk, I will introduce DensePose, our work on dense human pose estimation in the wild. Human analysis is one of the most central tasks in computer vision. And the most basic system one can think of is a classification system, which answers the question, is there a person in this image? Person detection is more granular, placing a bounding box around every human in the image. Part segmentation offers a more detailed understanding, associating image regions with body parts. What's currently commonly understood as human pose estimation consists in localizing joints of the human body. We argue that this can be substantially extended and enriched in terms of granularity. Rather than work with 10, 20 joints, in this work we interpret an image with a mesh having thousands of nodes. For this, we adapt a surface-based representation of the human body and establish correspondences between all human pixels on the image and the 3D surface. Our work is inspired by the exciting progress in interpreting 2D images in terms of 3D deformable models of the human body, such as a simple model. Starting from Simplify, it was shown that one can jointly estimate camera and statistical deformable model parameters, bringing model landmarks in correspondence with the 2D landmarks on the image. More recently, in this CVPR, Kanazawa et al. And Pavlakos et al. Estimate human shape by regressing simple model parameters with a convolutional neural network. In our work, instead of relying on simple at test time, we only use it to define the dense correspondence task. We then solve this entirely through discriminative training. In particular, we address the DensePose estimation with a single end-to-end trainable architecture that operates at multiple frames per second. To achieve this, we use a 2D parameterization of the human body shape. Since the human body as a whole is highly articulated, we partition it into many smaller and simpler patches. Each such patch is isometric to a plane. By flattening each patch with a multidimensional scaling, we associate every surface node to a local UV coordinate. So let's consider a single pixel. We localize it on the body surface in 2 steps. We first associate it with one of the 24 body parts. We then indicate precise position of this point on the surface using a 2D local coordinate system, the UV coordinates. By following this procedure on all image points, we establish a dense correspondence between the image and the surface. Turning to how we train a system to perform this task, our first contribution consists in constructing a large-scale dataset that allows for strong supervision. Here we visualize image-to-surface correspondence gathered for a single person. On the left, we have the cropped image and the points sampled by our system based on the parts provided by the annotators. On the right, we have the 3D model and the corresponding annotated points. Identifying these points manually can be time-consuming if done naively. So in order to scale up the annotation to all of COCO dataset, we introduce an efficient annotation pipeline. The proposed annotation pipeline has 2 stages. Firstly, we ask our annotators to segment images into semantic part regions. We note that we focus only on human body and ignore hair, clothes, or other accessories. We then sample a set of equidistant points within each semantic part region. We ask the annotators to bring each point in correspondence with the body surface. To do that, we provide 6 pre-rendered views of the body part, of a specific body part from different viewpoints. The annotator can freely choose among any viewpoint to pinpoint the surface point corresponding to each pixel. By using 2 stages and pre-computation, we avoid surface manipulation altogether. For each part, one can mark 14 correspondences in approximately 30 seconds. And we have collected such annotations for 50,000 persons in the COCO dataset and shared them through our project's webpage, densepose.org. We show some indicative visualizations from COCO that are colored based on U and V coordinates of the annotated points. For instance, the U coordinates of the torso, for the U coordinates of the torso, the color is changing horizontally. And for the V coordinates, the color is changing vertically. And we note that the annotations are obtained on a randomly sampled set of points. However, when performing this over 50,000 images, this provides sufficient supervision for the whole mesh. We evaluate the performance of our annotators using synthetic images from surreal data, for which we have ground truth coordinates since they were rendered by us. An example synthetic image is visualized with sampled and collected points from the torso. And we can measure the geodesic distance between the estimated and the actual node coordinates and average it over multiple images. So we can observe that our annotators are very accurate on regions with prominent visual cues such as hands, feet, and head, whereas parts such as upper legs and torso have larger errors. Collecting such a large scale and clean dataset has allowed us to use discriminative training for dense image-to-surface correspondence. For this, we follow the same principle as before. Every point gets assigned to a region, and then its local surface coordinates are estimated. Now, these 2 steps are addressed as classification and regression perspective. For this, we introduced the DensePose RCNN, a real-time system for DensePose estimation in the wild. We adopt the recent Mascarcian architecture and augment it with one new branch devoted to DensePose estimation. This is an 8-layer fully convolutional network that uses the features extracted from an ROI align layer and delivers 3 outputs. The first output classifies every node to one of the 24 model parts, and the other 2 regresses the U and V values within each part. We show here the predicted part indices and UV coordinates by the DensePose RCNN system for a YouTube video, involving multiple persons and heavy occlusions. Even though every frame is processed independently, the predictions are stable in time. So we compute our errors in terms of geodesic distances on the surface. For point-wise evaluation, we consider the ratio of correct points as a function of geodesic error threshold. And for per instance evaluation, we use the geodesic point similarity, a measure which is defined by us as the geodesic counterpart of the object key point similarity measure, commonly used for key points in COCO. We refer to our paper for more details regarding the evaluation. We start by inspecting the improvement we get with respect to model fitting approaches. We compare to Simplify 14 and Simplify 91 and observe a very clear improvement in accuracy, while being orders of magnitude faster. Clearly, the comparison is affected by us using strong supervision, so we can interpret this as showing the merit of our collected ground truth for discriminative training. In order to further compound the importance of having strong supervision, we compare the performance of DensePose trained using our collected DensePose COCO dataset versus surrogate datasets obtained by model fitting and synthetic images. This is achieved by training the system using rendered UV maps from simple models obtained from either the Surreal dataset, which has synthetic images, or the Unite the People dataset, which has simple model fitted to images. The results are obtained from the results that are obtained from the DensePose COCO dataset are clearly superior to ones that are obtained from the surrogate dataset. Having established the usefulness of our dataset and discriminative training, we turn to the impact of different architecture choices on the performance of our system. We summarize the performance using average precision metric, the counterpart of the one computed with OKS for key points in COCO challenge. We firstly note that using a larger network, namely ResNet 101, helps a little, but does not justify the cost in terms of computation time and memory. So all of our following experiments will therefore be done with the ResNet 50. By contrast, we obtain a substantially larger boost by multitasking. We make use of the fact that COCO dataset has other forms of supervision, such as masks and key points. Having additional tasks and treating them as auxiliary losses in the DensePose RCNN system substantially improves the performance. Especially having a head that localizes key points leads to an improvement of 1.8 points in AP. An even larger improvement is obtained by having information flow across different tasks. We do this by introducing connections between the blobs in heads that are responsible from different tasks and backpropagating through the resulting network. The cascading architecture improves the system performance quite a lot in terms of AP. We observe an improvement even when the task is cascaded within itself, and the improvement is most pronounced when the cascading with key points, leading to an improvement of 4.8 points compared to non-cascaded ResNet 50 baseline. Now turning to qualitative evaluation, we provide results delivered by our system. The results are shown in terms of isocontours of the U and V fields regressed by the DensePose RCNN. We note the robustness of our system to scale, occlusion, and variation in the appearance of the persons. We also note that the system has been trained with annotations aiming at the human body, and it successfully hallucinates the test time, the human body behind the skirt or the dress. Here we show similar results for our system operating on a video. These results are surprisingly smooth despite having been obtained on a frame-by-frame basis. Our system is running real-time on a single GPU and can handle multiple persons simultaneously. We have a real-time demo of our system at the Facebook booth in CVPR 2018. We demonstrate here how such a system can be used for tasks that go beyond key point-based human pose understanding. A toy application consists in performing texture transfer. Here we define the texture on the full 3D surface and then use the estimated dance correspondences to transfer it to the image. To conclude, in this work, we introduced DensePose, a method to establish dance correspondences between a single RGB image and a surface-based model of the human body. Our system operates in multiple frames per second and can handle multiple humans in the scene simultaneously. We make our code and dataset publicly available and are inviting you to participate in the DensePose Coco and DensePose Posttrack challenges that will take place in ECCV 2018. Thank you for your attention.
Thanks for the nice talk. Do we have any question in the room? So I do have a question, actually. So basically here you have a mapping between the image and the body surface. So what prevents you from visualizing the 3D mesh, as in the previous talk, for instance?
Because we're just estimating correspondences. Mm-hmm. We're not actually regressing the depth for the pixels. Okay.
So but since you have the mesh model, you could maybe have the 3D representation?
But we're finding correspondences between the image pixels and the template 3D model, not the specific 3D model reconstructed for that.
So you don't have the pose estimation or
we don't have the 3D pose estimation.
Yeah, okay. Yes. Okay, thanks. Do we have any other question? Okay, so let's thank the speaker again.
So the next talk will be Ordinal Depth Supervision for 3D Human Pose Estimation by Georgios, Pavlakos, Xiaowei, Zhou, Kostas, Daniilidis. Sorry for pronunciation. So please line up in the end for the questions. Georgios will present. Thanks.
Hello everyone, my name is Georgios Pavlakos, and today I will present our work on 3D human pose estimation from single images using ordinal depth supervision. So now allow me to switch gears a little bit compared to the previous presentation. Our input for this task is still a single color image of a person, but instead of handling only the visible points and estimating correspondences with the surface of a body model in a canonical pose, here our goal is to infer the 3D pose, to infer the 3D configuration of the human body by estimating the 3D locations for the most important body joints. What makes this problem harder for a data-driven approach is definitely the availability of data. While humans are very good at annotating 2D image properties of the human body, like 2D joint locations, segmentation, semantic part segmentation, or even dense correspondences, it is impossible for us to annotate metric 3D information. So if we don't have any 3D grounded for training, what data should we use for a task like that? A common solution is to leverage 3D pose data captured with mock-up systems in indoor laboratory conditions. By using these pairs of images and corresponding 3D poses, we can train networks end-to-end and achieve state-of-the-art results. However, this performance is mainly an effect of overfitting and makes our networks generalize very poorly in different conditions. Alternatively, prior work has proposed using synthetically generated images for training. And while you can generate more and even more of these images, there is an argument to be made that the domain gap between real and synthetic images remains very large. In fact, DensePose just now demonstrated that by adding these synthetic images in their training, actually deteriorated the accuracy of the correspondence estimation task. Finally, in an effort to use more realistic images, people, including myself, have proposed using multi-view data, since it's easier to generate automatic 3D pose ground truth, or you can learn 3D pose estimation directly by enforcing constraints of multi-view consistency. Well, I thought that myself that this was a very nice idea, and you could apply it to collect more data, maybe for golf, and running, and skiing, and even horse riding. And this could be very easy to scale up this data collection, right? Wrong. In fact, this would be a very laborious procedure, and at the end of the day, you would probably end up with a data set that is very limited in terms of variability compared to images you can find online. Why? Because in the wild images have this impressive variability that is so hard to replicate. This variability comes in terms of poses, and clothing, and background, and size of the person, and shape of the person, and color of the skin, and illumination, and shading, and objects of interaction, and facial expressions, and everything. So it is this variability that makes neural networks generalize so well. So yes, we do want to incorporate in the wild images in our training for 3D human pose estimation. However, as I said earlier, humans cannot annotate metric 3D information. But let us pause for a moment. Instead of focusing on what humans cannot annotate, let us think of what they can actually do. A human can look at this image, perceive the pose of the person, and infer that the right ankle is closer to the camera than the right knee. And similarly, the left wrist is closer to the camera than the left ankle, and so on. In other words, humans can annotate ordinal depth relations of the joints. And it is exactly this type of annotations that we gather in this work, and it is exactly this type of information that we use to train our neural networks. So in this work, we propose to substitute, or more accurately, complement the typical full 3D supervision with this weaker information signal provided by ordinal depth relations of the joints. But you may ask, why do we need ordinal depth relations? Well, in fact, ordinal depth has always been the missing link for 3D human pose estimation. Since the early days of computer vision, back in the 80s, people had identified that given 2D pose correspondences, you only need the ordinal depth relation for the adjacent joints of the kinematic tree to be able to fully reconstruct the 3D pose of a person. And now that we can actually localize 2D joints of humans on images thanks to deep learning, many of the errors for 3D pose estimation happen because of ordinal depth ambiguities. If we can train a network that learns to resolve these ambiguities, and this is exactly what we do in this work, then we should be able to greatly improve 3D pose estimation. Okay, this is great. How we can collect these annotations? Again, it is very efficient to collect ordinal depth annotations because humans only need to answer questions of the type, is joint A closer to the camera? Is joint B closer to the camera? Or are they at roughly the same depth? If the ordering of a pair can be inferred by previous answers, then we skip this question and we continue with the next pair. There are more details in the paper about design choices we made to accelerate the annotation procedure, but let me state here that we have collected ordinal depth annotations for more than 15,000 images from the LSP and the MPII pose datasets, and we have made these annotations available for research purposes. Okay, now that we have these annotations, how we can use them for learning purposes. First, let us assume that our network produces depth values Z1, Z2, up to Zn for n joints. For each pair of joints ij, we define a value R that indicates whether one of two joints is closer to the camera or if they are at approximately the same depth. Then, during training, we use a ranking loss, which has been proposed before for apparent depth estimation. Intuitively, if one of the two joints has been annotated to be closer to the camera, then this ranking loss maximizes their depth distance. Otherwise, if they are at the same depth, then the loss forces the depth values to be the same. Of course, this ranking loss is not only applicable for depth estimation, but it can be incorporated in the training procedure of typical neural networks for 3D pose estimation. For example, if our output is in the form of 3D pose coordinates, we can use the same ranking loss for the z values and apply a 2D key point loss for the xy coordinates, assuming we have 2D key point annotations. Similarly, we can handle other 3D pose outputs, like the volumetric representation we introduced last year. To clarify this part, we decouple the supervision on the 2D image plane and on the depth dimension. This is feasible by marginalizing over the z dimension to get the 2D heatmap of each joint, where we apply a typical heatmap loss, and also marginalize over the xy dimensions to get a one-dimensional depth distribution, where we apply the ranking loss that we discussed before. So going back to our network, from the voxel space, we can take the locations of maximum activations and infer the XYZ coordinates of the joints, where here, X and Y are pixel locations, and Z are ordinal depths. Do you see the asymmetry here? While our network predicts very accurately 2D zone locations on the pixel space and predicts depth values that respect the depth ordering, there is no correspondence to metric 3D because our network has never been trained with a single 3D pose example. To compensate for that, we introduce another component, which we call reconstruction component, and is responsible for the final 3D pose reconstruction. This component effectively performs a type of holistic reasoning by taking as input the 2D location of the joints and their ordinal depths and recovering a complete 3D pose. More importantly, this component can be trained using only mockup data. And remember that by taking a 3D skeleton, we can rotate it and project it in different viewpoints so that we can get 2D joint locations and ordinal depth and generate an abundant number of input-output pairs to train this network. Finally, the architecture for this component is a multi-layer perceptron, which has been proven to be a simple yet effective architecture choice for this type of reconstruction problems. So this is how our complete framework looks like. The first network is responsible to localize the 2D joints on the image and resolve all the ordinal depth ambiguities, while the second network takes this intermediate output and produce full 3D pose outputs. Let me now provide some more details about the empirical evaluation of our approach. First, we wanted, as a proof of concept, to demonstrate that that supervising our network with ordinal depth is competitive to using the full 3D ground truth. Here, we used the human 3.6 million dataset, and we trained different networks with these two kinds of supervision signals. Our networks were trained for depth regression, 3D coordinate regression, volume regression with 1 or 2 hourglasses, and across all these settings, ordinal depth supervision was competitive with full 3D supervision. Another interesting aspect of the ordinal depth supervision is that it can be used as a form of data augmentation for typical 3D pose datasets. Here, we took benchmarks that provide images with corresponding 3D pose ground truth, and we added in the wild images with our ordinal depth annotations as complementary supervision. This gave us significant benefits over the state of the art, achieving more than 10% relative error reduction compared to previous approaches. Moreover, our ordinal supervision can be particularly useful in cases with significant domain shift. Here, we use the same training data as before, and we applied our network on the MPI in 3DHP dataset without any fine-tuning. As you can see, besides achieving quite compelling 3D pose reconstructions, we also get state-of-the-art results for this dataset among methods that don't use any data from the benchmark for training. Finally, let me also demonstrate some more results from in the wild images. And here we compare with the simplify approach that uses only the 2D locations of the joints for the 3D reconstruction, which means that it cannot avoid errors due to ordinal depth ambiguities. In contrast, our approach leverages image-based information to resolve these ambiguities and recover a semantically correct 3D pose. However, as you can see, the output is still in the form of a stickman figure, so I believe that going forward, we need to think both about how to recover more image-based information to resolve this type of ambiguities, but also how to get more complete, more accurate 3D reconstructions of the human body instead of these simplistic stickman figures. As you see some more results from our approach, let me summarize the takeaway messages. First, I want you to remember that ordinal depth relations are a crucial cue for 3D pose estimation. They are easy to acquire and easy to incorporate in typical deep learning architectures for training. Ordinal depth supervision is a great form of data augmentation, and it improves a lot of results on standard benchmarks. And finally, I believe that ordinal depth supervision can open up the door for more accurate 3D pose estimation in the wild, and I hope that we can see more methods in this direction in the future. So with that, I would like to invite you to our poster to discuss in more detail our approach, and you can visit our project page to get code, the data we used, and the models, and we'd be happy to answer any question you might have. Thank you.
Thank you. Any question? There are 2 cameras in the middle. Microphone, sorry. Yeah. Well, this is computer vision, so. No question? Okay, so I had one question. Yeah, so I'm wondering how vague this task of ordinal annotation is for humans. So is it possible to see how humans are consistent with each other when you do this annotation?
Yeah, so we didn't perform like an empirical study on this aspect. What we based our motivation was a prior work from Christian Spincescu lab that demonstrated that humans could actually reenact 3D poses, so they could actually perceive and infer more or less accurately the 3D pose of other humans just from image evidence. So this was our motivation.
I see, but given the annotations that you already have, it's possible to look at the statistics to see how humans. Oh, but each person is annotated by only one person now, right?
Exactly.
Okay, I see. Thank you.
Thank you.
Thanks. So we are done with the oral, and now we are going to switch to spotlights. Is it already happening? Yeah.
Thanks. Good morning, everyone. Okay, I'm Pablo Speciale. I don't see the. And this project is a collaboration between two groups, ETH, Mark Polyface and Loop and Gould group, with the.
Meanwhile, we are still missing a few of the spotlight presenters, so please come to the front if you're presenting today.
Okay, let's start again. I'm Pablo. This project is a collaboration between two groups, ETH, so Mark Polyface and Loop and Gould group, with the participation of Danda, Martin, and Heiko. I want to explain with an example. So let's imagine that we have images with some semantics like window, doors, balcony, captured during the day and during the night. So the first step would be to have like the two separated reconstruction from these images that we want to align. Actually, this is the problem I want to solve. It's not related to analysis human, but and from these images, we get semantics, like as I was saying before, window mainly, and and that are fused in 3D, and then we can enclose this semantic with ellipsoids. We have two types of ellipsoids, like inner ellipsoids and outer ellipsoids. I will explain later, but essentially we are looking for a transformation that maximizes the number of ellipsoids inclusion from the source to the target, so from the inner ellipsoids to the outer ellipsoids. And our method get an initial alignment that we can further refine with ICP. That is the result that you can see now. One possible definition of ellipsoid is this one. I'm not entering detail, but having a point cloud, you can compute the convex hull. From the convex hull, you can get the inner ellipsoid that is the maximum volume ellipsoid inside the convex hull, and from the and then later the outer ellipsoid is the ellipsoid that encloses all the point in the point cloud. So what we are looking for then is a transformation edge, such as the inner. So here doesn't work well. The inner ellipsoid from a transformation that okay, let's move on. So our problem is a consensus maximization. So that what we are looking for is an in-layer set that we maximize the in-layer set, and in-layer set means that it's a correspondence in between the inner ellipsoid to the outer ellipsoid that is included. And so one possible example of this of our method is when you have two disconnected reconstruction, for example, outdoor and indoor, and of the same building. The structure for motion might fail, and what we share here is only the window information. Now we can use. So okay, so it's not working. So the CAD model so the other problem that we wanted to solve is CAD model and scan and the thing is here the reconstruction was the building was under construction and the windows were difficult to compute, so we have clear layers, but our method was designed to handle greater amount of layers, and well, that was the result that we get. So we invite you to join us to the spotlight to get the mathematical details, and so we will be Lambda, Pablo, Martin Oswald, and Pablo Speciale, me, in this poster session. Is C6 consecutive maximization for semantic region correspondences. Thank you very much. I'm sorry.
So, good morning, everyone. My name is Alessandro Vianello. I am from Bosch and the University of Heidelberg. And today I'm going to briefly introduce you our work, robust half-transform-based 3D reconstruction from circular light fields. So we are going to talk about light fields. Light fields are a technology that allows us not only to get the visual appearance of objects like normal camera do, but also the 3D information, so the geometrical information by acquiring the orientation of the light rays that these objects reflect or emit. We have two main ways to acquire light field. On one hand, we have some special camera with some micro lenses arrays. On the other hand, we can have some camera arrays, which is what we are going to use. Light field can be applied on various different applications, movie industry, consumer products, as well as industrial optical inspection, which is the topic that we focus on. An example that I show you here, it's linear light field. Linear light field, you can imagine to have a camera array or a camera moving linearly in front of a scene, and that's on the right what you get. It's this type of video or images. So in a linear light field, the important thing is that if you go in a bipolar domain, a scene point actually becomes a line, and the slope of these lines encodes the depth. So by finding the line, you can get the depth, and from the depth, a 3D reconstruction that you see here, which has actually some limitations. So limitation of linear light fields are that, as the name says, they are linear. So you can only reconstruct one side of the object with a linear light field. If you want to have a full 360 degrees reconstruction, you need to acquire 4 different light fields, linear light fields. And they also don't work with telecentric optics because we lose the depth effect. So we ask ourselves, can we do better than linear light field? And the answer is yes, by doing circular light fields, where we have a full 3D shape reconstruction with just one continuous acquisition. Now, how does a circular light field look like? You will see it here. That's a synthetic data set. That now it's, you see it still? I don't see it on my monitor, but anyway. It rotates 360 degrees in front of a camera, and then on the right you will see how a circular epi looks like. Now, it's not anymore a set of lines, but we have some curves that turns out to be sine curves. These curves actually encodes all the information we need for reconstruct the depth information. How do we do that? No deep learning. We use half transform, a very old method, but still very effective that can allow us to retrieve structure from an image. So we have this epi, we have a half space, and then from the half space, we find local maxima, and we reconstruct the phase and the trajectories of these trajectories. We compare it with the multi-view stereo. So briefly, I'd like to show you here the reconstruction. So blue means smaller reconstruction error, and our results on the right shows that we can get better reconstruction than multi-view stereo. Another interesting application of this circular light fields, since they are really robust against specular surfaces, is to analyze the intensity along trajectories. So this is a real data set, really specular objects. And if you see on the AP, you clearly see the 2 specular peaks. Now, if I plot, I visualize the trajectories, along the intensity along the trajectories, you see that we have this kind of behavior that actually says us, okay, we have 2 main lights. So these are really the specular peaks of the surface. And this we could use to do BRDF estimation, for example, for material classification. So to have a bit more depth talk and see more details, please come to my poster. It's on the C8. I'm happy to answer your question. Thank you.
Hello, everyone. I'm Chen Wu from USTC. I'm going to introduce our work with Cardiff University and NTU Singapore, a live caricature from 2D to 3D. As the title said, our target is generating a 3D caricature model based on 2D image. This problem inherited from 3D face reconstruction, but it's much more challenging. First, caricature styles are much more diverse than normal faces. Second, if we want to use something like shape from shading, it may not work because caricature's image is not reflect the real shading information. Third, if we want to use some blending method, it's hard to create a 3D caricature data set. So, how to solve this problem? We observed caricature has two constraints. And first, caricature can be recognized as human faces, so we call it a face constraint. On the other hand, the key difference between cartoon image and normal faces is exaggeration. We call it a caricature constraints. So, based on this observation, we proposed a optimization problem and to solve this generation problem, and including two terms. First term was face constraint, and to make our generated face like a face. Second term, we use a 2D landmark to control exaggeration. I'm focused on the first terms. We proposed a new representation of 3D faces from deformation view. Suppose we have two meshes with the same topology. We can find a paired vertex between them, like the red points on the nose. So we check the wandering neighborhood of them. To capture the local deformation between this local structure, we compute the deformation gradient between them. Then we use the polar decomposition to decompose the T into two separate parts, rotation parts and the scaling or shear parts. To allow linear combination between these two parts, we compute the logarithm of R and the shift S with identity matrix. We use these two items to compute the local deformation. Apply this process to each vertex pair. We can represent the deformation between these two models. Apply this whole process to a 3D face data set. We can generate a deformation base. Our face constraint is making our generated face can be represented by this new deformation representation base. And here comes the comparisons. At first, we compare it with linear representation, face 3DMM, and binary representation, face warehouse. We find that their method cannot get good result because the target face was beyond their scope. And we also removed the regularization term of 3DMM, we call it 3DMM minus. And we find that the mesh quality is very poor. We also generate many caricature model and represent them by 3DMM. We call it a caricature 3DMM. And, but we also find their result is not as good as we wanted. And by the way, our method can get a better result compared with them. So make a further comparison. We apply as rigid as possible deformation based on previous result. And we also find our method can get a more natural result compared with them. So more examples. In summary, a new representation work for extremely fast. Welcome to C10 for our poster. Thank you very much.
Good morning, everyone. I'm Luan from Michigan State University. Today, I'm going to present our work on nonlinear 3D face morphable model. Given a face image, 3DMM model try to explain it by using different components like shape, texture, and projection, where the shape, texture are the linear combination of the basic function. Traditionally, the 3DMM is learned in supervised fashion by doing dimension reduction on the 3D scan, which is very expensive and laborious to obtain. Also, for the texture, they use the 3D image co-capture with the 3D scan to learn the model, which is in controlled environment, and it limits the application of the 3D model. Finally, the representation power is also limited by the linear assumption of PCA. So in this work, we will try to learn a nonlinear model which can leverage class collection of 2D images and also leverage the power of deep neural network. As a result, we can have a better reconstruction for the in-the-wild image. Let's revisit the linear model. So their formulation can be seen as a matrix multiplication. So in the neural network point of view, it's a single fully connected layer without any activation. Naturally, we can replace it with the deep network like CNN or multi-layer perception. So here how we learn it. For the encoder, we'll estimate the projection and shape and texture representation. So the representation can fit to the decoder to get the shape and the texture. With the novel rendering layer, they can be combined to the reconstruction image. So the network will try to make the reconstruction as close as possible to the input image. We also have an adversarial loss to make the reconstruction to be more realistic. And also we use the landmark loss to realize our learning. So this is some result on our model. Here we show how the shape, the texture, and the rendering image change by modifying one element in the shape representation or the texture representation. By modifying the shape, we can see the face structure or the impression change. And when modifying the texture, it can change the skin tone, it can grow in beard or change in the lighting. Finally, we show some application in monocular 3D reconstruction. Thanks for the nonlinearity, we can robustly handle the facial hair, and as a result, it can have a better 3D reconstruction. We also show some comparison with theory at all. It's an unsupervised 3D regression method. Even though they learn in the wide image, they still be limited by the linear model so that they cannot handle the beard. And as a result, their surface can be distorted in the wide texture. Also, we compare with CLI or high quality 3D reconstruction. Even they can add the detail into the 3D surface. They still limited by the linear model and cannot handle the peer or other linear, non-linear variant. Thank you.
Hello everyone, I'm Min from MIT. I'm sure you have heard a lot about human pose estimation this morning. What I'm going to tell you about today is how to do it through walls and occlusions. This is joint work with my colleagues from MIT. Occlusion is a fundamental challenge for all computer vision tasks, including human pose estimation. Existing algorithms cannot work when the person is behind the wall. What we want to do is to see the pose through walls, but how can we do that? Interestingly, wireless devices we're using every day actually transmit a signal that can traverse through walls. Those RF signals also reflect off our human body because our human body is full of water. Our idea is to use such RF reflections to estimate human pose through walls. Let me first show you how RF signals look like. RF signals can be represented as vertical and horizontal heat maps, indicating where the reflections are coming from. As you can see, while the person is walking, the peak on the heat maps moves with him, even when he's behind the wall. We want to train a neural network to estimate the pose from the heat maps. But one question we have to ask first is, how can we get a labeled data set? In fact, it's almost impossible for human to annotate RF with key point. So how can we train a model to do so? Here's how we're going to do it. We use vision to provide cross-model supervision. During training, we collect synchronized RGB images and RF measurements. We can extract confidence maps of key point from RGB images. and those confidence maps will be used to provide supervisory signals to the student network. The student network uses RF as input and is trying to get the same confidence map. Once the model is trained, we can use RF signals only to estimate the confidence maps of body key points. Human poses can be further extracted by applying non-maximum suppression and association methods based on confidence maps. To train such a model, we went ahead and collected 50 hours of data at 50 different locations around our campus. During the experiment, people were going about their own life without much interference from our side. Now let me show you the output of our model on the test data. As you can see, it gave the poses through walls. In fact, if you think about it, it's quite interesting. It's able to get the pose through wall, despite that it's never been trained with such examples, because its teacher cameras cannot see through walls. Here is another example when people are walking behind boxes, posters, and other types of occlusions. It also works in bad lighting conditions. As you can see, there are two people walking in the dark, and our model is able to capture the pose of those two people. Note that none of these examples are possible with current vision-based algorithms. Now I want to show you how our model handles different activities. As you can see, it's able to capture people when they are writing on the board or sitting and talking. Here's another environment when people are taking downstairs and our model is working effectively. For more information, please visit our website or stop by at our poster. That's all, thank you.
Hi everyone, I'm Dean. Today I'm going to talk about our work on analyzing the temporal information in video models. This is a joint work with my internship mentors at Facebook and advisors at Stanford. Videos contain much more than just the images. If we look at the image, we might think that the tiger is attacking the person. However, if we play the video, we can see that the tiger is just being playful. In order to build systems that can really understand videos, it is therefore important to utilize temporal information. And this is exactly what a lot of recent approaches do, including two-stream, 3D convolution, and a lot more. The question is, do these models really capture temporal information? We're the first to provide an explicit answer to this question. In other words, our goal is to quantify the effect of temporal information in a video model. Here, C3D trained on UCF 101. We'll achieve this by not changing the weights at all. First, we get the performance from the original video. We then use the proposed framework to remove the temporal information from the test video and compare the two, resulting no temporal performance. The gap between the two is our estimate of the effect of temporal information. If the gap is really small, then we can say that C3D trained on UCF 101 is not really using temporal information. The goal is to push this performance as high as possible to get a tight estimate. The first and the most naive approach is to just pick a single frame from the video. In this case, it is just an image and there's no temporal information. We then replicate the frame as input to the model. With this, we see that there's a pretty big gap, but we cannot conclude that the temporal information is important. There can be multiple reasons for this gap. One possibility is that the model has never seen a static video before and can be confused. We address this by proposing a temporal generator. Using GAN's terminology, you can think that the generator is trying to fool the C3D by generating a video from the image without using any real temporal information. For more details on the generator, please come to our poster. This closes the gap by 15%. Another thing that might affect the performance is the frame we pick. there might exist a keyframe for us to easily recognize the action without using temporal information. We thus propose motion invariant frame selector to select a better frame without using temporal information. And this further closes the gap and allow us to give a 6% upper bound on the effect of temporal information in C3D trained on UCF 101. This is much tighter than where we started. One thing we found in our analysis is that frame selection is actually quite important. Therefore, we further analyzed the upper bound of frame selection by using the ground truth label to find the best possible oracle frame. To our surprise, the upper bound can actually outperform the original video. This indicates a quite interesting direction in keyframe selection. To conclude, we show that video models do not see videos as we do. In particular, we provide a much tighter upper bound on the effect of temporal information, 6%. We further show that keyframe selection can be quite important. Please come to our poster at C16 for more details. Thank you.
Good morning. I am Seung from Yonsei University. In this paper, we introduce a best method for semi-supervised video object segmentation. This is a joint work with Junyoung and Kaiwen at Adobe Research and my advisor, Sanju Kim. The problem is defined as follows. Given video frames and the ground truth object mask for the first frame, the goal is to estimate all the object mask for all the remaining frames. Recently, many deep learning approaches are proposed for this task and achieves remarkable accuracy. However, we believe that their speed is way below the criteria for real video editing use case. This slowness is mainly attributed to additional training step called online learning that fine-tune the network parameters on test video at test time. On the other hand, our method achieves accuracy comparative with state-of-the-art method without online learning while learning in a fraction of time. To avoid online learning, we first propose a new network structure that combines strengths of previous detection and propagation-based approaches. And we also propose two-stage training to effectively train our network with small video training data. Propagation-based method usually take the current frame image and previous object mask as an input and estimate the current object mask. In this setting, network runs the temporal coherence to propagate the object mask. Detection-based method usually make use of a reference image and independently detect the target object at every frame. In this setting, Siamese network runs the appearance of the target object to match them across video frames. On the other hand, our method take both the previous object mask to be propagated to the current frame and the reference frame that specify the target object to be detected in the current frame. In this setting, our method can simultaneously make use of the temporal coherence of motion and the appearance of object without online learning. To effectively train our network with small video training data, we first pre-train our network using simulation data generated from static images to generate two video frames that contain same target object. One of random transform and image composition is performed. After pre-training, we fine-tune our network on video. During fine-tuning, we make recurrence like RNN by feeding the previous output as of current input. Training losses are computed at every intermediate estimation and backpropagated through time. These are our results on Davis. As you can see, our method is applicable for both single and multiple object segmentation. And you can find more details and more results on our poster session. Thank you.
So due to some technical difficulty, we're gonna continue with 9, and then 8 is gonna happen in the end of the session.
Everyone, what you're seeing here is a system trained on the charades dataset, doing home activity recognition in real time on a webcam. How do we get the next huge boost on this task? I'm Gunnar Sigurdsson, and this is our work on understanding human activities from both third and first person. Theory of mind, that is, people understand other people by putting themselves into their shoes, is important for understanding activities. But there's no such dataset where we can peek into the mind of the actor, and all ecocentric datasets are only in first person. To address this challenge, we introduce our new dataset, Charades Ego. We can see that the pairs of videos are representative of our daily lives and contain different kinds of information about what is happening. This is inspired by and a continuation of our Charades project, an activity recognition dataset released in 2016. We propose understanding activities from both first and third person at the same time. Following our Hollywood and Holmes method, we had people record themselves both in third person and then record the same videos again in first person. But how do random people on the internet record first person videos? Maybe holding a phone against their head? Actually, it turned out that over 70% of the videos were submitted courtesy of a homemade head mount, as seen here. Our new dataset, Charades Ego, contains 8,000 videos in both third and first person with 68,000 annotated activities and is publicly available. We learn a common model where we're connecting those two worlds, such that we could, for example, utilize all the third-person supervision available in the web for ecocentric recognition. We encourage the model to learn semantics, not only matching the motion. Many frames are not easily alignable as seen here, and we address this by finding good frames to learn from. These are all frames selected by our model, good and bad. Our objective is to find the right first-person frame given a third-person frame. We accomplish this by minimizing the distance between the correct frames and maximizing between wrong frames. We minimize a ranking loss over all triplets by also learning to select triplets to learn from, where capital P is a learned distribution. This is the selector which finds good frames. To understand what the model is learning, we look at activations before the fully connected layers. This model has no motion information. We can see that in the first person, the model is focusing on the center of the field of view and particularly objects. In the third person, the network is focusing on the person and particularly what is in front of the person, the field of view, the hands, and so on. To demonstrate our model, we have 3 experiments, such as using the third-person supervision in the charades dataset to do zero-shot ecocentric recognition. For more information, please come to our poster or visit our website. Thank you.
Hello everyone. Here we present a hierarchical structure adaptive for the video summarization task. The authors are from China. The first author, Bin Zhao, is from the Optimum Lab of the Northwestern Polytechnical University. The second and the third author are all from the Chinese Academy of Sciences. Actually, this work is based on the assumption that the video data follow a hierarchical structure. while a video is composed of shots, and a shot is composed of self-frames. In this case, we develop a structure-adaptive video summarization approach that integrates the shot segmentation task and the video summarization task together. Here is the diagram of the proposed HSA. It contains two layers. Layer 1 and layer 2 are both bidirectional attempts designed to exploit the video structure and generate the video summary. Note that the attempt in layer 1 operates in a sliding manner to detect shot boundaries, and the stride at each step is equal to the length of previous detected shot. The dashed boxes in the first layer indicate the locations of detected shot boundaries. Layer 2 captures the inter-shot temporal dependencies and is utilized to predict the shot level probability. Overall, the main contributions of this paper are: first, an approach jointly explores the video structure and summarize the video content. Second, a sliding bidirectional LLTM is designed to detect shot boundaries. Third, the results show the superiority of HSA on shot segmentation and video summarization. As aforementioned, HSA contains two layers. The first layer is the video structure exploitation layer. The bidirectional LLTM operates on the video frames in a sliding manner and tries to detect shot boundaries step by step. As shown in Fig 2, compared to the long single LLTM, the sliding bidirectional LLTM is much shorter, which can mitigate the vanishing gradient problem by avoiding extremely long temporary dependency exploitation. The second layer is the video summarization layer. This layer is also bidirectional LLTM. Given the first layer outputs as input, it is utilized to capture the forward and backward temporal dependency among shots. Then the forward and backward hidden states, together with the encoded shot features, are jointly employed to predict the probability of each shot to be selected into the summary. Then we present some results. Here are the results on shot boundary detection. We can see that the sliding bidirectional LLTM perform much better than current shot segmentation approaches utilized in the summarization task. Then we present the results on the summarization task. We can see that the proposed HSA gets the best performance on the 4 popular datasets, including SUMME, TSUM, COSUM, and VTW. Then we present some summary examples. The bars below the frames indicate the frame information. The long gray bar stands for the whole video stream, and the short blue bar denotes the selected key shot. The fourth and fifth are generated by output and ground truth, which are quite similar. Further questions can be at the poster at D2. Thank you.
Today we will introduce our work, Fast and Accurate Online Video Object Segmentation via Tracking Parts. This is a joint work with UC Merced, NEC Labs, and Qionghai University. Video object segmentation aims to separate a target object from background and other instances on the pixel level. Given the initial mask of the target object, algorithms track and segment these objects throughout video. Many state-of-the-art algorithms use convolutional neural network to do this. They usually tackle this problem in 2 steps. In the first step, a foreground segmentation network is trained considering all the objects in training data. This model will separate generic foreground objects from the background. And in the second step, the network is trained to focus on the particular instance by heavily fine-tuning on the initial mask. Experiments show that this fine-tuning step is a key factor in such methods and contributes a lot to the performance. However, this step is time-consuming and is not suitable for the online application. For multiple target object segmentation, it requires one model for each instance. Based on this observation, we propose to develop a fast algorithm by replacing this fine-tuning step with tracking-based algorithm. To construct a tracking-based method, there are two challenges. First, for instance-level tracking, state-of-the-art trackers cannot always follow the objects tightly, especially when there is fast object deformation, like the dancer in this video. And secondly, for pixel-level tracking, optical flow can be used to propagate the foreground pixels, but the error may accumulate fast over time, and the segmentation can easily get divergent. To tackle these two challenges, we decompose this problem into two subtasks, part-based tracking and ROI segmentation. For part tracking, we generate some representative parts from the first frame and its initial mask. Then we track each part independently throughout video. During part tracking, we design a ROI segment to predict object segmentation for each part. Finally, we aggregate this part segmentation to get the final object mask. On the left-hand side, we show some example of the generated parts. And on the right, the yellow box denotes our aggregated part tracking result, and the green box denotes the results using tracking the entire object. Comparing these two results, our method can better handle challenges with object deformation and occlusion. Here are some examples of our part tracking and the final object segmentation results. We show that the proposed algorithm can handle objects with deformed shapes, cluttered background, occlusions, as well as fast object motion. This figure shows the runtime versus accuracy trade-off for state-of-the-art methods. We present two versions of the proposed method, with and without dense AI post-processing. Compared to methods that fine-tunes on the first frame, our method achieves comparable performance and is much faster. In conclusion, instead of using time-consuming fine-tuning step, we propose to use part tracking and ROI segment for fast and accurate video object segmentation. The proposed algorithm can immediately start segmenting target object once given the initial mask. We hope it's a new direction for balancing speed and accuracy for video object segmentation. Our code and models are now available on GitHub. Thank you very much.
Hi, everyone. I'm Zhou, and I'll present our work on predicting 4D effect in videos, opening exciting avenues in bringing 4D cinema to your home. This is joint work with Makaran and Sangya. 4D movies give the audience an immersive and interactive movie watching experience, with a chair shaking in a car chase and water splashing when the boat breaks through the waves. However, there's little work on bringing 4D effects to traditional 2D or 3D movies. After 3 days, this is you now. But imagine if your seats are controlled by a neural network. We introduce a new and challenging task of automating 4D effect prediction. To do this, we first collect the movie 4D dataset. For example, in Avatar, imagine that you are Jake taking down the aircraft. You experience the light and heat from the explosion, and also a mild wind and shake while flying the Quran. Our datasets consist of several effect types. Global effects, such as weather, are applicable to a group of people, while others, such as shake, are more character-centric. The camera viewpoint is used in a standard 4D setting. For example, in this clip, we will feel the heat as the One Ring is revealed. We go beyond and also annotate effects experienced by main characters. This has the potential to allow each person in the audience to relive their favorite character's moments. A 4D experience is all about the details. For example, the direction in which your chair shakes is critical for an authentic feel. To enable this feature, we also teach our model to predict effect-specific details. For example, in this clip, Frodo pulls Sam out of the water. Audience members who live in Frodo will experience a physical interaction, a mild splash from the front, and a left-to-right shake due to the rocking boat. We annotate 63 movies, 700 clips, and obtain almost 9,300 effect labels. Each effect lasts for around 6 seconds, and 12 effects are annotated in each clip. Similar to action recognition, we address two tasks: classification of effect and all details given a short clip, and detection of effect in a long 5-minute clip. we adopt a multi-model neural network for classification. We process audio-visual information through several pre-trained networks and concatenate their features. We use separate MLPs for classifying effects and their details. In detection, video frames are grouped into shots. We obtain camera and track level prediction by processing corresponding video regions. Finally, we perform a joint inference over the entire clip by promoting co-occurrence between shots and camera track predictions. We present some key results. For effect classification, our model achieves an accuracy 4 times that of random. In the more challenging task of effect detection, our model achieves an average precision of 57%. This indicates the difficulty of our problem. We present an intense clip for predictions. GT refers to the ground truth, while the unary and CR predictions are shown below. Notice we also predict the details. The clip contains multiple effects happening to different characters simultaneously, and our model is able to successfully find them. We invite you to take on the challenge of automating 40 effect prediction. For more details, please stop by our poster at D6. Thank you.
Hi, my name is Atsushi Kanehira from University of Tokyo. I will introduce our work, viewpoint-aware video summarization. Viewpoint changes how the video looks. When we are given a video in which the running event is taking place in Venice, when we focus on the place, the video may look like this. But the viewpoint changes to the kind of activities. The same video may look totally differently like this. A different viewpoint has different similarities. In the same examples, when we focus on the place, the video of running Venice is more similar to shopping Venice than running Paris. But the relationship will get reversed when the viewpoint changes the kind of activities. So our task in this work is to estimate the underlying viewpoint given similarities. In other words, we would like to know what makes that similarities. In this work, we utilize predetermined groupings as similarities, such as user preference, good and bad. To show output will result on the video summarizations. It extracts the subset of frames from all videos simultaneously. And as a requirement, the extract summary should reflect the similarities. In other words, it should be representative to other videos in the same group and discriminative against other videos in the different groups. Our method is very simple. First, we consider the visual feature of summary V, which can be obtained by multiplying the X and Z. X is a matrix that stacks all shot features, and Z is an indicator that corresponds to each shot. Inspired by Fisher criteria, we minimize a combination of 3 variances defined by the visual features. Each term corresponds to the age requirement, and the loss function can be optimized with concave convex procedure. In order to compare the different algorithms, we create novel dataset. We firstly collect a set of video using 3 keywords, so that video can be divided with 2 explicit viewpoints. In this case, video can be divided with the place and kind of activities. The target video have 2 different annotations summaries, so that each corresponds to 1 viewpoint. In this case, the video running in Venice has the 2 different types of summary, Venice and running. And we compared predict summaries with ground truth to evaluate. Using that set, we conducted some experiment. As a matrix, we utilize mean average precision. From these tables, we can see that our method outperforms other baselines, including the other video summarization method, which only takes representative information. And from the user studies, we can see that our method is the best in the qualitatively. If you are interested, please stop by our poster. Thank you.
So we will now have the last spotlight, the number 8, due to technical difficulties we had to. It's okay. Yeah. Is China? Okay. Thanks.
Okay, I will just play it from my laptop. So this is the spotlight on neural network Viterbi. So we propose a framework for weakly supervised video learning that should unify a bit more to standard deep learning issues. The problem in general is we are given a video and we want to find a segmentation in the temporal domain, meaning in this example we have like 4 different segments that we are supposed to find that can be labeled with background if we are not interested, or with like eating, drinking, like some action classes of interest. And of course for each of these segments we also need the length. So with this we would have a full segmentation of the video. So essentially we want to find the segmentation that maximizes the posterior probability given the video. Luckily there is a good solution to solve this, which is the Viterbi algorithm. But the problem is usually training, because we rely on like 2 quantities. One is the ordered action sequences that occur, which are pretty easy to obtain. Either in some cases you can infer them from video subtitles, or in other cases you can just use a human annotator who can just quickly skim through the video and see what actions happen. But the length are actually very hard to obtain, and even human annotators frequently do not agree where an action ends and where the next action starts. So we want to get rid of this quantity for training and train only on the segmentation, meaning we are given just the ordering, background eating, background drinking, plus the video, and we do not know the length during training. So this is essentially the setup. And methods that tackle this problem so far usually use a kind of iterative approach where you take a training video and you use a uniform segmentation of all the actions you are given, like illustrated in this example. You do this for all your training videos, so all training videos will just be uniformly segmented, and you define this as your pseudo ground truth. Then you have some system, a deep neural network, you train it on this pseudo ground truth, and you hope that it learns something reasonable. You use the network to refine this pseudo ground truth to get a better segmentation, and so on and so on. You iterate until convergent. The big disadvantage of this is essentially that if you make large errors in this initialization, you will propagate them throughout the whole training. So we want to propose a model that is much closer related to the standard approach for deep learning, where we usually have the steps of forwarding something through the network, computing a loss, and then do backpropagation. And we do not want to be relying on this kind of pseudo-initialization. So what we do is essentially we forward the video through a neural network, and we will get a probability distribution over the possible action classes for each frame. So this would be like the first forwarding step. Next step to come is the loss computation. Loss computation is difficult because we do not have any frame-wise annotation in our training data. So we use the Viterbi algorithm to align the ordered action sequences according to the frame-wise probability the network outputs. And with this frame-wise alignment, we can essentially put the result into a cross-entropy function, or a cross-entropy loss. So we can compute a loss function and then just backpropagate through the video. So you see that we already have like this classical 3 steps now: forwarding, loss computation, backpropagation, and we are not relying anymore on this ugly case of pseudo ground truth where we have this uniform initialization at the beginning. There are some issues if the videos are very long. We cannot crop the videos during training because we do not know where. We do not have temporal annotation. So we may overfit to the appearance of a long video or to the classes that occur in a long video. But we have solutions for that, and I will tell you about that on the poster. As a very last thing, I will give you a short preview of the effectiveness of our approach. So compared to current methods that use the same kind of supervision, we can improve by 10% absolute, which is quite significant. And code is also available online if you want to mess around with it. Yeah, and I hope to see you at the poster. Thank you very much.
Okay, this concludes our morning session. So let's thank all the speakers again.